All right, so in this next example, it says Blowing Baubles, a company that makes hand-blown glass items, has a marginal revenue function of R prime of X dollars per bauble when X thousand baubles are produced and sold. The graph of R prime is shown below. We want to use a right-hand Riemann sum with 4 subintervals of equal width to estimate the net change in revenue when the number of baubles made is sold and increases from 2,000 to 18,000. So the key here is that we're looking at a marginal revenue function, not a revenue function. And remember, the marginal revenue function is a derivative specifically of your revenue function. So this is not the graph of the original R of X. This is the graph of R prime. And based on the discussion that we had towards the end of the last video, the area under a curve where the curve is a derivative of something from A to B, whatever that interval on the x-axis is, gives you the net change in the original function over that interval. So here it says that X is being measured in thousands of baubles, and we're increasing from 2,000 to 18,000 of these things. So because X is measured in thousands, 2,000 will look like 2 on the x-axis, and 18,000 will just look like 18 right there. So we want to use a right-hand Riemann sum with 4 subintervals to approximate that area that would give us that net change. So let's first look at what delta x is. We typically start there. Since we're going from 2 to 18, delta x would be 18 minus 2 divided by the number of subintervals, which is 4. That's 16 over 4, or just 4. So starting from 2, we want to count by 4s. 2 plus 4 is 6, plus 4 is 10, plus 4 is 14, and then we have 18. So here are the 4 subintervals that we care about. We're using a right-hand Riemann sum, which means I use the right endpoint of each subinterval to construct these rectangles. So it's going to go like this, and then we're going to have one here, and then we'll have one here, and then this one is equal to 0. So even though I don't have a function that I can plug values into, I can easily come up with the right-hand Riemann sum for this thing, because the y coordinates of these endpoints that I'm using are all given to me. The y coordinate of this point, for example, would give me the height of that rectangle, and then the y coordinate of this point would give me the height of that rectangle, and so on and so forth. So when I do the Riemann sum, it's delta x times f of 6, f of 10, f of 14, f of 18, and that's really just those values that are given to me there. So 4 times, let's start with the first right endpoint. It has a height of 48, plus over here I have a height of 40, plus this y value is 16, plus this one, which is just 0. So if we did the arithmetic here, this comes out to 408. Now, this is a word problem, so we should use units of measure here. And at the end of the last video, we talked about how to get units of measure from an area where we know the units of the curve and we know the units of our x. So the units of r prime are dollars per x thousand baubles, and x is measured in just 1,000 baubles. So the revenue, which is what this represents, would just be dollars, $408. Again, that's just an approximation because we don't have the true area under this curve. We just have an approximation for it. Okay. All right, let's keep moving. So far, all of the functions that we have looked at, when we're trying to find an area between the curve and the x-axis, all of those functions have been positive on the intervals that we have found that area over. What that means is that the curve would be above the x-axis in all of those cases. However, we know from our experience with graphing that that's not always the case. Different functions will give you curves that go above the x-axis, below it, or both, like this example here. So we need to kind of interpret what it means for a function to have area between a curve and the x-axis if part of that function is below the x-axis. And the way that we do it is any area that's counted below the x-axis, it's counted as negative. So in this example, we would have these blue rectangles that go above the x-axis. Those are counted as positive, and the yellow ones will be counted as negative. Now that makes sense when you consider the fact that, kind of like in this last example, the heights of these rectangles are given by y values of those endpoints. So really what we're doing is we're multiplying our delta x by each of the y coordinates of those points. But if you're talking about a curve that goes below the x-axis, the y-coordinates of all of the points that determine these yellow rectangles would be negative numbers. So we're multiplying delta x, which is always positive, by negative numbers down here, which gives us negative values. And that's why this ends up getting counted as negative area. Okay, so sometimes we refer to that as net area because we're going to, if we want the total area from A to B in this example right here, we would add all of the positive area with all of the negative area. And because you have positive and negative happening, there's going to be some cancellation that happens. In fact, if the amount of area in the blue is the same as the amount of area in the yellow, except that the yellow would be counted as negative, then the sum of all of that would be 0. So it is possible for a function to have an area of 0 between the curve and the x-axis, even if you see area there. Okay, and again, it has to do with that net area idea, where some is negative, some is positive. So let's apply this to an example here. We want to find the area between the line y equals 2x minus 3 and the x-axis on the interval negative 10, 5, using a left-hand Riemann sum with 5 subintervals of equal width. For this example, I could easily draw this graph because that's just a line and it's a relatively easy one to graph. But I've said it before, you don't actually need to sketch the graph if you understand this process. It's helpful to sketch the x-axis at least, but aside from that, I don't need to worry about any other part of this graph, like the curve. So start by putting the interval down. We're going from negative 10 to 5, and then let's figure out what delta x is. So subtract upper endpoint minus lower endpoint, 5 minus negative 10, divided by the number of subintervals, which in this case is 5. Okay, that would be 15 divided by 5 would give me 3. So we're counting by threes. Negative 10 plus 3 would be negative 7. Plus 3 is negative 4. Plus 3 is negative 1. Plus 3 would be 2. And then plus 3 would give me that 5 right there. So I can see that I have these 5 subintervals. We're using a left-hand Riemann sum. So within each of these subintervals, I only want to use the left endpoint. Those are the numbers that I'm going to plug into this function. Okay, so to do that, let's work this out. I know that I'm multiplying the f of each one of these by 3, so I can factor that 3 out, and then I'm going to have 2x, so that's 2 times negative 10, minus 3 here, plus 2 times negative 7, plus 3, plus, and you know, I'm going to go like this, dot, 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 plus. Because I could write out all of them, but you kind of get the idea. I'm plugging each of these left endpoints into that function until I've gone all the way up to 2 here. So that would be the last one, 2 times 2 plus 3. Like that, okay? Now, oh, sorry, these should be minuses. Those are minuses. That's what the function's telling me. We've done something kind of like this before, but imagine that you're doing a problem like this. You forgot your calculator. You don't have, or you just don't want to punch all of this into your calculator. We can use some mental math techniques or some simplification techniques to help with this. So I'm not going to do this all the time, but it's helpful to do it sometimes just to show you how it works. If you look at what's in here, you can drop these outer parentheses, and I have minus 3 showing up a bunch of times. In fact, it will show up 5 times because there's 5 subintervals to account for. So 5 times negative 3 is another way of adding those up 5 times. that would just be negative 15. I'm going to hold on to that in my mind because I want to deal with these other terms first. If I deal with the minus 3's, then what's left is 2 times a number, 2 times a number, 2 times a number. I can factor the 2 out of each one of those, and I'm left with just the sum of the numbers that were in those parentheses, which is really just all of these left endpoints that we started with. Negative 10, minus 7, minus 4, minus 1, plus 2, because we stopped at 2, right? So that is what the sum of all of those 2 times a number is going to look like. And then the minus 3's we said would add up to negative 15. Okay, let's continue working through this. So I have negative 1 plus 2, which is positive 1, plus negative 4, that would be negative 3. Negative 3 plus negative 7 is negative 10, plus another negative 10 is negative 20. Multiply that by 2, and I'm going to have negative 40 minus 15. That's negative 55, and 3 times negative 55 is negative 165. Okay, so this is my end result. And notice that it's negative, right? So what that would mean is that the majority of the area trapped between this curve and the x-axis on that interval is below the x-axis. It doesn't mean that all of it is below the x-axis. It just means that there's more negative area than there is positive area, so that the net of that would be a negative. So that's another example. Let's now move on to the definition of the term that we titled this section with, and that's the definite integral. In section 4.1, we introduced the indefinite integral, and we basically just said that all that is another way of saying find the most general antiderivative of a function. But now we're going to define something called a definite integral, which has very similar notation. It has a very similar name, indefinite integral and definite integral. But the definition is going to seem to have nothing to do with antiderivatives at all. It turns out those two things are definitely connected. Otherwise, we wouldn't give them such similar names and notation. But the real connection is going to be explored in section 4.4 in our next section that we cover. So for now, we're going to treat this as though it's a different thing, even though it looks very similar. So we'd say, here's our definition. If f is a continuous function, then the definite integral of f from a to b is the net area of the regions between the graph of f and the x-axis on the interval ab. So basically what we have been doing this entire time is we have been finding areas between a curve and the x-axis, and as of the last example, we can now make sense of that, even if the function f of x gives us a curve that goes below the x-axis as well. We call that net area. So whatever that net area is, that is what we're defining the definite integral of f over that interval to be. Up until now, we've only been doing approximations of those areas using a rectangular approximation method, with the one exception at the beginning, a couple of exceptions actually, at the beginning of this lecture where we can use geometric area formulas to get exact areas. But for the most part, we've been dealing with approximations. However, we did see all the way back here, I'm going to find that picture for you again. Where is it? We saw all the way back here that the more rectangles you cram under that curve, the better that approximation for the area gets. Remember, the number of rectangles corresponds to the number of subintervals, which we typically denote by n to be general. So if this area gets continually better as n gets larger, the number of subintervals, then we would expect that if you took the limit as n went to infinity of that Riemann sum, remember that adds up those areas for those rectangles, then that should make that area go from an approximation to an exact area. And that's what ends up happening. So this summation right here is our rectangular approximation method for when we have n subintervals, but if we take the limit as n goes to infinity, it's no longer an approximation, it's an exact area. And that is defined to be this, the definite integral. Notice in the definite integral, the lower and upper or the left and right endpoints of the interval you're finding that area over are indicated there. The smaller one is down at the bottom, the bigger one is at the top, and we refer to these numbers as the lower and upper limits of integration. Okay? So now that we have a meaning behind that symbol in that term, let's start using it. So I would like to use the graph shown here, y equals f of x, to evaluate the integral, the definite integral, which oftentimes we'll just say the integral, from -6 to 4 of f of x dx. Okay, so first of all, again, we have seen this symbol before, this for indefinite integrals. The way that you know that you're looking at a definite integral instead of an indefinite one is if those numbers appear there, if you have those limits of integration. So I don't have a representation of f of x algebraically, I just have a graph to look at. Let's refer to the graph. We want to start at -6, which is here, and go all the way to 4, which is here. This is one of those examples where I can find the area between this curve and the x-axis using just area formulas. So notice, if I were to cut this thing up into a few different pieces like this, then I could think of each one of them as a simple geometric figure that has a basic area formula. So let's do what we've done before, call that A1, A2, A3, A4. I have two triangles, two rectangles. So for A1, the area is 1/2 times the base times the height. The base here goes from -6 to -3. That's 3 units, so 1/2 times 3. And then the height is also, well, no, it's not 3. It goes from 0 down to 4, so that would be 4. Okay, but there's one other important thing to pay attention to. This area, or this figure, is below the x-axis. And if it's below the x-axis, like we said before, we count that as negative area. In fact, that's the case for all of these figures. So I need to make sure and put a negative there to account for that being negative. Okay, 1/2 times 4 is 2, times 3, that would be 6. Okay, same thing for A2 through A4. So A2, make it negative. It's a rectangle, and the dimensions of that rectangle are 4 by 4. So really, it's technically a square. Length times width, that's going to be 4 times 4. We're counting it as negative. Forgot to put my negative there. That makes this -16. Okay, A3, another rectangle. This is a 1, 2, 3 by 1, 2, 3, 4. So it's going to be -3 times 4, which is -12. And then A4 is a triangle. It's a smaller triangle. It's got a base of 3 and a height of 2. So we're going to say -1/2 base times height. 1/2 times 6 is 3, but it's negative. And then we add these, and the total area is the sum of all of this. So let's see. This would be -22, -34, -37. Okay? So notice this doesn't feel a whole lot different than what we've been doing this entire time. The purpose of this example was to show that this notation represents something that we've already been doing, but now we're just getting used to using this notation and understanding what it means. Also, it was another example where we had to remember the difference between negative area and positive area. Okay, so with that, let's take a look at another example where we're doing the same thing. We're doing a definite integral, but we're using a table of values instead of a graph or something like that. So here we are asked to take this table, which gives us values of f of x for a variety of different values of x, and we want to use it to approximate this integral, the definite integral from 6 to 8 of f of x dx, but using 5 subintervals of equal width. And you'll notice it says A here. I took this one from the book. There was a part B as well. I didn't want to do both parts because they were so similar. So that's why we're only seeing the A here. But as has been the case, anytime we're estimating the area under a curve, we find delta x first. So we're looking at the interval from 6 to 8. That means I'm going to do 8 minus 6 divided by, again, the number of subintervals, which is 5. So 8 minus 6 is 2, divided by 5 would be 0.4. I'm using decimals because I'm seeing decimals in my table. Okay, so now what I want to do to get a sense of where the endpoints for my subintervals live, I'm going to make a note of the fact that I'm going from 6 to 8. And we're going to count by 0.4s because that's my delta x. So 6.4, 6.8, 7.2, 7.6, and then 8. Okay? Where we're using 5 subintervals, which we now see, of equal width, and we're using a right-hand Riemann sum. So for each one of these subintervals, I use the right endpoint. This one, this one, this one, this one, and this one. So what this means is that my integral, my definite integral from 6 to 8 of f of x dx is approximately, I have to use approximately because we haven't taken a limit of the sum that we're going to evaluate. We're just using the rectangular approximation method, which is not the exact area necessarily. But I know that it's equal to delta x times the sum of f of each one of these. So delta x is 0.4. And then I look to the table. So 6.4 is here. That's my x value. When I plug it into f of x, I get -4. Then 6.8. So in fact, I'm going to circle the ones that I need. 6.8 is next. That gives me 1, so I add a 1. 7.2 is next. That gives me a 0. Add a 0. 7.6 is next. Plug that in, I get a 2. And I also need 8, so this one right here. When I plug an 8 in, I get an 8 out, so that's +8. Okay, this is pretty easy to work out. When you compute all of this, you're going to end up with 2.8. Okay, pretty straightforward. All right, so now that we have gone through all of this work of finding these areas and defining this definite integral idea, we need to talk about some of the properties that definite integrals have. So these are relatively straightforward to understand if you think of everything in terms of area. We'll just sort of talk through each one. So for all of these, we're going to assume that f and g are continuous functions on the interval a, b. Okay, first of all, first property, if you take an integral where the lower and the upper limits of integration are the same number, notice there's a c here and then there's also a c here, that will always equal 0. And the reason for that is because if you think about a curve like this, normally you need a left and a right endpoint of your interval, say something over here, so that you have some amount of area between those two endpoints. But if the lower and upper limit of integration are the same, you're basically looking at a line going up to that curve, which has no area. So the area is 0. This next one, if the limits of integration are the same, then there is no area. Oh, I read that already. If you're integrating f of x from a to b, that is equal to the opposite of the integral from b to a of f of x. Now, where that comes from is actually that delta x term. Remember, delta x is defined to be the upper limit of integration minus the lower limit of integration divided by the number of subintervals. So if you're looking at the interval from a to b, then you're going to do b minus a over n, right? But this is the same thing as negative a minus b over n. And that's easy to verify. If you bring that negative into the numerator, you switch the signs in the a and the b, and then you can switch their places as well, you would get back to this. So what I've effectively done, though, is by switching the order of these, I've switched which number is the upper limit and which one is the lower limit, and I got a negative out of it as a result. So that would happen in the case of this integral as well, because that delta x appears in the definition of that integral, and that negative comes all the way out of that summation, all the way out of that limit, and it sticks with you once you get that integral there. So in other words, reversing the order of your limits of integration will change the sign of a definite integral. This next one, if you have the definite integral of a sum of two functions or a difference of two functions, the result is the definite integral of f of x dx plus or minus the definite integral of g of x dx, depending on whether this was a plus or a minus. So in other words, you can take a sum of functions that you're integrating and split it up into a sum of two integrals, or a difference will split into a difference. This is not hard to see why this is true if you think about it in terms of areas, but we're not going to go through an argument for it here. I'm just going to state that result. Similar here, if k is a constant, if you're taking the definite integral of a constant times a function dx, and the integral goes from a to b, you can take constants that are being multiplied to functions in the integrand and pull it out of the integral. So in other words, you're only integrating f of x, getting an area from that, and then multiplying it by that constant. We'll see how that works in an example. Finally, one last case. If you're integrating a function from a to b of f of x dx, that is the same as integrating from a to c, and then adding that to the integral from c to b of that same function. And this is not hard to see why this is true either. Imagine I have an interval from a to b, and somewhere in between there I have this c. If I want the area from a to b, which is all of this right here, that's what this first integral represents. The limits of integration are a and b. It goes through that entire interval. These two integrals only represent parts of these areas. If I take the integral from a to c, I would get this first area, and then if I take the integral from c to b, I would get the second area, and by adding them together, I'm putting both areas together to give me the total, which is why it's equal to this. Okay, this is even true even if that number c is not in the interval ab, even if it's way out here. And it's not hard to prove that, but it's not really worth the time either. Okay, I'm going to do this example in the next video.